Look into the eyes of a chimpanzee, and something feels strangely familiar. The face is different. The body is different. The movements belong unmistakably to another animal. And yet, behind those eyes, we recognize something. Curiosity, attention, calculation, perhaps even emotion. That feeling is not an illusion. Humans are apes. We did not descend from the chimpanzees or gorillas alive today. Instead, humans and the other living apes inherited different branches of a much older evolutionary tree. Somewhere millions of years ago, populations that shared common ancestors began following separate paths. Over immense stretches of time, those paths produced chimpanzees, bonobos, gorillas, orangutans, and us. And genetically, the distance between humans and our closest living relatives is surprisingly small. But the consequences of that distance are enormous. Chimpanzees live in complex social groups. They recognize individuals, form alliances, compete for status, care for offspring, hunt cooperatively, use tools, and learn behaviors from one another. Some populations even develop local traditions that are passed through generations. None of these abilities belongs exclusively to humans. That is what makes the question so fascinating. If intelligence exists in other apes, if tools exist in other apes, if cooperation, emotion, communication, and even culture exist in other apes, then what exactly happened in our own lineage? Why did one ape eventually build cities, write mathematics, reconstruct the history of the universe, and send machines beyond Earth? For a long time, people searched for a single dividing line. Perhaps humans were the only animals that used tools. Then scientists observed chimpanzees modifying sticks to extract termites, using stones to crack nuts, and employing leaves as sponges to collect water. Perhaps language was the dividing line. But other primates communicate through complicated combinations of vocalizations, gestures, facial expressions, and body movements. Their communication is not human language, but neither is it simple noise. Perhaps cooperation made us unique, yet chimpanzees cooperate during hunts, defend territories together, and build political alliances inside their communities. Perhaps empathy separated humans from animals. But consolation, caregiving, and responses to distress have been documented in other apes as well. Again and again, traits once believed to create an absolute boundary turned out to have evolutionary roots extending far deeper into the past. The difference between humans and other apes therefore appears less like a single wall and more like a collection of changes that gradually amplified one another. Our bodies changed, our brains changed, our childhood changed, our social lives changed. The way we learned from one another changed, and eventually, the amount of information that could survive from one generation to the next became extraordinary. To understand this, we have to return to Africa, long before anything resembling civilization existed. More than 6 million years ago, the ancestors of humans and chimpanzees had not yet become the species we recognize today. Their populations were evolving in changing African environments containing forests, woodland, and more open habitats. At some point, different populations became increasingly isolated from one another. There was no morning when one group suddenly became human. Evolution does not work that way. Generation after generation, tiny differences accumulated. Some disappeared, others spread. Populations divided and sometimes mixed again. Entire branches evolved for millions of years and eventually vanished. Human evolution was never a straight ladder leading inevitably toward us. It was a branching tree. For much of that history, several different human relatives existed at the same time. And one of the earliest major transformations involved something that seems almost ordinary today, walking on 2 legs. Other apes can stand and move upright for short distances, but humans became unusually committed to habitual bipedalism. Over time, The pelvis, spine, legs, and feet of our ancestors changed in ways that made upright walking increasingly efficient. This transformation began millions of years before the enormous human brain appeared. That detail matters. We did not become intelligent first and then stand upright. The story began with bodies that were changing long before anything like modern human cognition existed. Bipedalism altered the relationship between the body and the environment. Hands were no longer required for ordinary locomotion on the ground. They could carry food, infants, and objects. They could manipulate the environment while the body moved independently. But free hands alone did not create humanity. Chimpanzees possess remarkably capable hands. They manufacture and use tools without building technological civilizations. Something else would have to change. Over the next several million years, our ancestors experienced a complicated evolutionary experiment involving diet, social competition, cooperation, environmental instability, and increasingly flexible behavior. Early members of our lineage still possessed brains much smaller than ours. Then, particularly within the genus Homo, average brain size began increasing substantially. But even this does not provide an easy answer. A larger brain is expensive. Human brains consume a remarkable amount of energy relative to their size. Large brains also create developmental problems. Human babies must grow enormous amounts of neural tissue after birth, meaning that our young remain dependent for years. Evolution would not maintain such an expensive organ unless it produced significant advantages. Those advantages were probably not one single ability. Instead, larger and reorganized brains interacted with social living, tool use, communication, planning, and learning. And this is where the human evolutionary path begins to become extraordinary. Imagine an animal that can learn something new, that is useful. Now imagine an animal that can watch another individual and copy what it has learned, that is even more powerful. Now imagine that the copied behavior can be improved, remembered, taught, and passed to another generation. At that point, evolution gains a second system of inheritance. Genes still pass biological information from parents to offspring, but culture begins passing learned information between minds. And unlike genetic evolution, cultural change can sometimes move astonishingly quickly. A stone-cutting technique does not have to be rediscovered independently by every individual. Knowledge can survive the person who first discovered it. One generation can begin where the previous generation ended. This ability, sometimes described as cumulative culture, would eventually become one of the most important features of human life. No individual human being invents civilization alone. We inherit languages we did not create, technologies we did not invent, stories we did not witness, and knowledge produced by people who died centuries before we were born. A modern human child enters a world already containing thousands of years of accumulated information. That may be one of the deepest differences between us and the other apes. Not that humans alone think, not that humans alone feel, not that humans alone communicate or use tools, but that human minds became extraordinarily interconnected across individuals, communities, and eventually generations. To understand how that happened, however, we first need to examine something more fundamental: the body of the strange ape that eventually became us. The human body still carries the history of its ape ancestry. Our hands, shoulders, eyes, teeth, skeleton, and even the way our muscles are arranged all preserve traces of a body plan that evolved long before humans existed. But evolution did not simply replace the ape body with a human one. It modified what was already there. That is one of the most important ideas in evolutionary biology. Nature does not design organisms from scratch. It works with inherited structures, changing proportions, functions, and developmental patterns over time. The human hand is a perfect example. At first glance, it may seem uniquely suited for precision. Our thumbs are relatively long and mobile. We can oppose them against the fingers, grip small objects, rotate tools, and perform movements requiring extraordinary control. But the basic structure of the hand is ancient. Chimpanzees, gorillas, and orangutans also possess grasping hands with nails instead of claws. The difference is not the presence of the hand itself. It is how that hand became integrated into a different way of life. Our ancestors gradually became more committed to walking on two legs. As that happened, the hands became less involved in locomotion and increasingly available for carrying and manipulation. This probably did not immediately lead to sophisticated technology. For millions of years, early hominins likely used natural objects in simple ways that left little or no archaeological trace. A stick used once and discarded can disappear completely. A leaf folded to hold water leaves almost nothing behind. Even stones can be used without being deliberately shaped. That means the archaeological record almost certainly preserves only a fraction of ancient behavior. The earliest known stone tools are already evidence of something important. A stone deliberately struck to produce a sharp edge is not just an object. It is evidence of planning. The maker must understand, at least in practical terms, that one object can be transformed into another. A useless stone can become a cutting edge. A carcass can become food more efficiently. Bones can be broken open. Plants can be processed. Materials can be altered. That is a small technological step by modern standards, but an enormous cognitive one. Still, stone tools alone did not make humans unique. Other animals also modify objects. Chimpanzees prepare sticks for termite fishing. Some birds shape hooks. Sea otters use stones to break shells. Tool use is part of a wider evolutionary spectrum. What became unusual in humans was the increasing complexity, flexibility, and transmission of technology. Human tools did not simply become better, they became part of systems. A stone could be selected from a particular source, it could be transported, it could be shaped in a specific sequence, it could be combined with wood, fiber, resin, or bone. And crucially, another person could learn the process. This required not only dexterity but attention. A learner had to watch. An expert had to tolerate being watched. Movements had to be repeated. Errors had to be corrected. Eventually, skills could become traditions. This may sound ordinary, because modern humans grow up surrounded by teaching. But deliberate teaching is not equally developed across species. In many animals, young individuals learn largely by observation and trial. Humans increasingly turned learning into a social activity. And that created a powerful feedback loop. Better learners could acquire more complicated skills. More complicated skills rewarded better communication. Better communication allowed more effective cooperation. More cooperation created larger networks for sharing knowledge, and larger networks made culture more stable. The human difference may therefore have emerged through interaction, rather than through one dramatic mutation. Hands, brains, communication, and social organization evolved together. At the same time, another major transformation was occurring in the face. Compared with other apes, modern humans have relatively small jaws and teeth. Our faces are flatter. Our canine teeth are reduced. The massive chewing structures seen in some earlier hominins are absent. Part of this change probably reflects diet. Food processing reduces the physical work required by the jaws. Cutting food into pieces changes how much force is needed. Pounding and grinding plant material changes texture. And later, cooking would transform food even more dramatically. Cooking softens many foods, changes proteins and starches, reduces chewing demands, and can increase the energy available from some foods. The control of fire, therefore, may have affected much more than warmth and protection. It may have influenced anatomy, digestion, daily schedules, and social behavior, but the exact timing of habitual fire use remains difficult to reconstruct. Evidence becomes stronger in later periods, while earlier claims are often debated. What matters is that human evolution increasingly depended on technology changing the environment before the body encountered it. This is unusual. Instead of waiting for teeth to evolve that could process every food efficiently, our ancestors could process food outside the body. Instead of evolving thicker fur for every cold environment, humans could eventually use fire, shelters, and clothing. Instead of evolving claws, we made cutting tools. Instead of evolving extreme speed, we developed weapons and cooperation. Technology began functioning almost like an external extension of anatomy. A spear extends the arm, a container extends the ability to carry, clothing extends the skin. Fire extends the body's ability to remain warm. And once technology becomes culturally transmitted, adaptation can happen much faster than genetic evolution alone. This helped humans move into environments that earlier hominins could not easily exploit. But technology also created dependence. A human without culture is not simply a fully formed animal missing a few conveniences. Much of what allows us to survive exists outside the individual body. We depend on knowledge inherited from others. How to make tools, how to find food, how to recognize danger, how to care for infants, how to navigate landscapes, how to cooperate with strangers. The human body, in other words, evolved inside an increasingly cultural world, and one of the clearest signs of this is our unusual childhood. Young chimpanzees remain dependent on their mothers for years, but human children take dependency much further. We are born neurologically immature compared with the adults we eventually become. The human brain continues enormous amounts of growth and reorganization after birth. Children require food, protection, teaching, and social contact for a very long time. From a purely energetic perspective, this is expensive. A slowly developing child consumes resources for years before becoming fully independent, yet evolution maintained this strategy. Why? Because long childhood creates time for learning. A species that relies heavily on inherited knowledge benefits from giving young brains enough time to absorb it. Children learn language. They learn social rules. They learn which foods are safe. They learn how tools work. They learn who can be trusted. They learn what their community remembers. And because human environments can change rapidly, a flexible childhood may be more useful than being born with rigid solutions. This produces one of the great paradoxes of our species. Human infants are among the most helpless young mammals relative to the abilities of adults, yet that helplessness is connected to one of humanity's greatest strengths. Our brains are unfinished, and because they are unfinished, they are extraordinarily open to the world around them. A child born thousands of years ago could learn to track animals across a landscape. A child born today can learn to read, use computers, understand maps, or operate machines that did not exist in any previous generation. The biological brain changes slowly across evolutionary time. But the information placed into that brain can change almost instantly by comparison. This flexibility became one of the foundations of human success. Yet it also created a problem no individual parent could easily solve alone. Human children were becoming too demanding. They needed too much food, too much protection, too much time. Raising them successfully increasingly required help, and that pushed human evolution toward an even deeper dependence on other people. Humans did not become successful because individuals became independent. In many ways, the opposite happened. Our species became increasingly dependent on cooperation. A lone human is physically unimpressive compared with many large animals. We are not especially fast. We do not have claws. Our teeth are small. Our skin offers little protection. Even our children remain vulnerable for years, yet groups of humans can accomplish things no isolated individual could manage. They can surround prey, defend territory, share food, protect children, care for injured members extant information, and divide complicated tasks between many people. This cooperative lifestyle did not appear fully formed. Its foundations are much older and can be seen in other apes. Chimpanzees form alliances. They groom preferred partners. They cooperate during some hunts. They remember previous interactions. They can support allies during conflicts and compete intensely for social position. Human social behavior grew from this primate foundation. But over time, our lineage seems to have pushed cooperation in unusually flexible directions. One important difference involves food sharing. When many animals obtain valuable food, competition follows immediately. Chimpanzees sometimes share meat after hunts, but access can depend heavily on status, relationships, and persistent begging. Humans developed far more extensive systems of sharing. Among hunter-gatherer societies, large or unpredictable foods are often distributed across multiple individuals or families. This reduces risk. One hunter may fail today and succeed tomorrow. One family may find food while another does not. Sharing turns unpredictable individual success into more stable group survival. That matters enormously in environments where food availability changes from day to day. It also creates social obligations. If someone shares with you today, you may be expected to help later. Human cooperation therefore became connected not only to immediate reward, but to memory, reputation, and expectation. We remember who helped us. We notice who refuses. We care how others see us. We respond strongly to fairness and cheating. These psychological tendencies are deeply important because cooperation is fragile. A group works only if individuals do not exploit one another indefinitely. If everyone takes but nobody contributes, the system collapses. Human societies developed many ways of controlling this problem: praise, shame, reputation, reciprocity, punishment, exclusion, and eventually formal laws. Even in small communities without written rules, social behavior is constantly observed. Humans are intensely interested in what other humans are doing. Who is trustworthy? Who is generous? Who is dangerous? Who broke a promise? Who helped during a crisis? Who deserves support? This attention to reputation may have placed strong pressure on social intelligence. Living with other humans means navigating a world filled with invisible information, relationships, bentictions, obligations, rivalries, alliances, kinship.tosake, promises. A socially successful individual must remember not only what happened, but who did what to whom and why it matters. That may help explain why human intelligence cannot be understood simply as problem-solving ability. A brain that can solve physical problems but cannot manage relationships may struggle inside a highly cooperative society. And as social groups became more interconnected, another major change became increasingly important. Cooperation expanded beyond close relatives. This is remarkable. Many animals cooperate strongly with kin because relatives share genes. Humans certainly do this as well. But humans also cooperate extensively with unrelated individuals. We trade with strangers, work alongside people we barely know, participate in institutions containing thousands or millions of members, sets resources to people we may never meet, follow rules created by individuals who died long ago. Such large-scale cooperations depends on abilities that other apes possess only in much more limited forms. Shared expectations, common identities, symbolic communication, norms, and trust in systems larger than personal relationships. But long before states, religions, or markets existed, cooperation probably expanded through smaller networks. Neighboring groups could exchange materials. Individuals could move between communities. Marriage could connect families. Information could travel far beyond the place where it originated. Archaeologists sometimes find stone materials hundreds of kilometers from their geological sources. Such objects can reveal something important. Ancient humans were not always living inside isolated local worlds. Objects moved, and when objects move, people or relationships often move with them. A rare stone may pass from one group to another. A tool-making technique may spread. News about water, animals, or danger may travel across social networks. These connections can make populations more resilient. Imagine two groups experiencing different conditions. One suffers a failed hunt, another has access to food. If relationships exist between them, resources can potentially move. Now imagine drought, fire, disease, a local ecological collapse. A broader social network can provide alternatives. Where individual survival once depended mainly on local knowledge, humans increasingly gained access to knowledge stored across many minds. This may have made social networks almost as important as physical tools. A sharp stone helps you cut meat. A trusted relationship may keep you alive during a famine. And cooperation affected human childhood as well. Because children require so much investment, mothers often receive help from fathers, grandparents, siblings, and other members of the group. Researchers sometimes describe humans as cooperative breeders, although the exact pattern varies between societies. The essential point is that human child rearing frequently involves more than one caregiver. This can transform family structure. A mother who receives reliable help can support dependent children differently from one who must provide everything alone. Grandparents may contribute food, care, or knowledge. Older siblings may help younger ones. Fathers may invest directly. Other relatives and community members may also participate. This network of care allows childhood to remain long, and long childhood allows more learning. Again, the same feedback loop appears. Cooperation supports learning. Learning improves cooperation. Culture becomes richer. Sure, culture makes prolonged learning even more valuable. Over generations, biology and culture begin shaping one another. But cooperation did something else. It allowed humans to specialize. In a group, every individual does not need to perform every task equally well. One person may be better at tracking, another at making tools, another at identifying plants, another at remembering distant water sources, another at caring for children. Specialization creates efficiency, but it also creates dependence. The better a group becomes at dividing labor, the less completely self-sufficient each person needs to be. Modern societies take this to an extreme. Most people today survive using technologies they could not manufacture themselves. We eat food grown by strangers, live in buildings built by specialists, use electricity generated by systems few of us understand completely, rely on medicine created through knowledge accumulated across countless generations. The principle, however, is ancient. Humans succeed by distributing knowledge. No single brain has to contain everything. The group can function as a larger cognitive system. This may be one of the most important differences between humans and other apes. A chimpanzee can be extraordinarily intelligent, but chimpanzee knowledge remains limited by the structure of chimpanzee social learning and cultural transmission. Human intelligence increasingly became collective, and once minds could connect through more precise communication, that collective intelligence would become vastly more powerful, because cooperation has limits when information is difficult to transmit. You can watch someone make a tool. You can imitate a gesture. You can follow another person to food. But there are things observation alone cannot communicate easily. Yesterday, tomorrow. A place beyond the horizon, an animal that is not currently visible, a person who is absent, a plan that has not happened yet, a danger remembered from years ago. To share information like that, Humans needed something more. They needed language. Language changed the scale of human cooperation. Before language, information could already pass between individuals through observation, gesture, facial expression, and vocal signals. Other apes do this today, but human language created something far more powerful. It allowed information to become detached from the immediate moment. A person could describe something that was not present. A water source beyond the hills, an animal seen yesterday, a danger expected tomorrow, a person who had broken an agreement, a place remembered from childhood. Once communication could refer to things beyond the here and now, social life changed dramatically. Planning became more precise, teaching became more efficient, coordination became easier, and knowledge could travel farther than direct experience. The origins of language are difficult to reconstruct because speech leaves no fossils. There is no ancient sentence preserved in stone. No archaeological layer marks the first conversation. Researchers, therefore, have to study indirect evidence, anatomy, brain organization, genetics, school-making, social behavior, and comparisons with other primates. None of these can tell us exactly when language began, but together they suggest that language did not appear suddenly. It probably emerged gradually from older systems of communication. Modern apes already possess many of the building blocks. Chimpanzees use different vocalizations in different contexts. They gesture intentionally. They monitor the attention of others. They can alter behavior depending on what another individual appears to know or see. Bonobos are highly sensitive to social signals. Gorillas and orangutans also use complex combinations of posture, facial expression, touch, and gesture. The ancestral ape from which humans evolved was therefore almost certainly not silent or socially simple. Communication was already important. What changed in the human lineage was its precision, flexibility, and combinatorial power. Human language can produce an effectively unlimited number of messages from a limited set of sounds or signs. The same words can be rearranged to produce completely different meanings. A few symbols can describe an event that has never happened. They can express uncertainty, possibility, intention, deception, memory, rules, and imagination. That ability transformed cooperation because humans no longer had to learn everything by watching. Someone could explain, imagine making a stone tool. Without language, a learner must carefully observe where the stone is held, where it is struck, and how much force is used. With even a simple spoken system, the teacher can direct attention. Hit here, turn it, not that stone. Use this edge, try again. Language does not eliminate imitation, but it makes teaching far more efficient. It also allows information to be compressed. A person who spends years learning an environment can transmit important parts of that knowledge to someone who has never experienced the original events. This can include dangerous animals, seasonal patterns, plant properties, travel routes, social relationships, and techniques that took generations to develop. In this sense, language became a technology for transferring experience. A brain could benefit from events it had never personally witnessed. That alone would have enormous survival value. But language also changed the structure of groups. Human societies depend heavily on coordinating behavior around shared information. Where will we meet? Who will go? Who will stay? What happened? What should we do if something goes wrong? Who owes whom? Who can be trusted? These questions become easier to manage when communication is precise. Language also makes reputation portable. Without language, knowledge of another individual may depend mainly on direct observation. With language, information about a person can spread through the group. Someone can describe generosity, Keating, courage, aggression, really ability, or betrayal. This creates a powerful social environment. An individual's behavior can affect how people treat them, even when those people did not personally witness the original event. Human cooperation therefore became linked not only to what we do, but to what others say about what we do. This may have strengthened social norms. Rules no longer had to exist only as repeated behavior. They could be stated, remembered, explained, and eventually justified. Children could be told not merely what to do, but why. Adults could discuss conflicts, groups could negotiate, and collective expectations could survive far longer. Language also allowed humans to create categories. This may sound simple, but categories are extraordinarily powerful. Instead of remembering every individual plant separately, people can group similar plants together: edible, poisonous, medicinal, seasonal. Instead of treating every animal track as a unique shape, hunters can connect patterns to species, direction, speed, and age. Words give stable labels to recurring features of the world. That makes knowledge easier to organize and transmit. Language can also represent things that do not physically exist: a boundary, a promise, a debt, a marriage, a rule, a role. These exist because people collectively recognize them. This ability to coordinate around shared concepts would later become essential to large human societies. But its roots may be much older. Even small groups depend on expectations that cannot be touched. Who belongs here? Who is related to whom? Who is allowed to use a resource? Who has responsibility for a child? Who owes assistance after receiving help? Language gives these invisible relationships structure. And once symbols become important, another transformation becomes possible. Humans can begin constructing shared worlds of meaning. An animal is no longer only food. It can also become a symbol. A place can become associated with ancestry. An object can represent identity. A burial can express a relationship with the dead. A mark can carry information. At some point in human evolution, archaeological evidence begins showing increasingly clear signs of symbolic behavior. Pigments were collected and processed. Objects were decorated. Shells were sometimes perforated and worn. Engravings appeared. Burials became more elaborate in some populations. These behaviors do not all prove language by themselves, but they reveal minds increasingly capable of representing meaning beyond immediate practical use. The human world was becoming symbolic, and symbols have a remarkable property: their meaning can be shared. A mark means nothing unless minds agree that it means something. Language works the same way. There is nothing naturally connected between a particular sound and the object it represents. Meaning depends on convention. A community agrees, usually unconsciously, that certain sounds, gestures, or signs refer to certain things. Children absorb these conventions from others. The system therefore exists not inside one brain, but across a population. That is another reason human intelligence became collective. Language belongs to individuals, but no individual invents an entire language alone. Each generation inherits one. It learns the vocabulary and structure created before it was born. Then it changes that system slightly and passes it onward. Languages evolve culturally. Words appear, pronunciations shift, meanings change, grammar changes. Languages divide, others disappear. This process can happen far faster than biological evolution. And once language existed in sufficiently flexible form, human culture gained a powerful memory system. Knowledge no longer needed to remain tied to direct demonstration. Stories could preserve information. Instructions could become traditions. Experiences could become warnings. Events could become shared history. Before writing, everything still depended on living memory. The Great Pyramid. But living memory could now stretch across generations. An elder could describe events that happened before younger people were born. Children could learn routes they had never traveled. A community could remember disasters long after the original witnesses died. human groups were beginning to accumulate not only tools, but narratives, and narratives can organize behavior. They tell people what happened, what matters, who belongs, what is dangerous, what should never be forgotten. At this point, the difference between humans and other apes becomes easier to see. It is not that other apes lack communication. They communicate constantly. It is not that they lack intelligence. They solve difficult problems. It is not that they lack culture. Different ape populations maintain different learned traditions. The difference is scale. Human language dramatically increased the amount, precision, and complexity of information that could move from one mind to another. And once information could move efficiently, culture could accumulate much faster. That accumulation would eventually transform nearly every aspect of human life. But it depended on something even more basic. Humans had to become exceptionally good at understanding other minds. One of the most unusual features of the human mind is that we constantly try to imagine what other people know, not just what they see, not just what they are doing, but what they believe, what they want, what they intend, what they may be hiding, and what they might do next. This ability is so familiar that we barely notice it. If someone reaches toward a cup, we assume they want the cup. If a person looks repeatedly toward a doorway, we may suspect they are waiting for someone. If a friend suddenly becomes quiet after hearing certain news, we try to infer what they are feeling. Human social life depends on this kind of mental interpretation, but psychologists often describe part of it as theory of mind, the ability to represent the mental states of others. Humans are not the only animals that respond to what others can see, know, or intend. Experiments and observations suggest that great apes can track some forms of attention, goals, and knowledge. But humans develop these abilities to an extraordinary degree. We spend enormous amounts of mental energy thinking about other minds. This matters because cooperation becomes far more sophisticated when individuals can predict one another. Imagine two hunters approaching an animal from different directions. Each person must understand not only the prey, but the partner. Where will the other person move? What are they trying to do? Have they seen the animal? Do they understand the plan? Should I wait? Should I move? Successful coordination requires minds that can continuously update expectations about other minds. The same ability is essential in teaching. A teacher must recognize what the learner does not yet understand. If the learner makes a mistake, the teacher must identify where their understanding differs from the intended result. This sounds obvious to us, but it requires a remarkable cognitive process. The teacher is effectively comparing two representations of the same task: what I know and what I think you know. Human communication becomes much more powerful when this distinction is possible. It allows explanation, correction, persuasion, and deception. The ability to understand other minds has a darker side. A species capable of sophisticated cooperation is also capable of sophisticated manipulation. To lie effectively, you must understand that another person can hold a belief different from reality. To hide information, you must anticipate what someone else is likely to infer. To manipulate an alliance, you must understand relationships among several individuals at once. Human social intelligence therefore evolved inside a world containing both cooperation and competition. The same mind that helps a friend can deceive a rival. The same ability that allows empathy can also allow strategic manipulation. This tension is not uniquely human. Other apes also compete politically. Chimpanzees form alliances that can alter access to status and resources. Individuals may support one partner against another. Relationships can shift. Past interactions matter. But humans expanded these social networks dramatically. We can track relationships between people who are not currently present. we can discuss those relationships with others, and we can coordinate around them using language. This creates social worlds that exist partly inside shared memory. Consider a small group of perhaps several dozen people. Each individual may have a different relationship with every other member: parent, child, sibling, friend, rival, partner, ally, competitor. Now imagine keeping track not only of your own relationships, but also of relationships between other people. Who trusts whom? Who is angry with whom? Who helped whom? Who is related to whom? Who may support whom during a conflict? The number of possible relationships grows rapidly as groups become larger. Social life becomes a complicated information problem. A larger brain can help process that complexity. This idea is part of what researchers call the social brain hypothesis. It proposes that the demands of managing complex social relationships contributed to the evolution of larger primate brains. The hypothesis does not explain every aspect of human brain evolution, and researchers continue to debate exactly how ecological and social pressures interacted. But the broader point is clear. Human intelligence evolved in a deeply social environment. Our brains were not shaped only by solving physical problems. They were shaped by living with other brains. And that may explain something striking about human attention. People are extraordinarily sensitive to faces. We detect faces rapidly. We notice where eyes are looking. We distinguish subtle changes in expression. Even newborn infants show strong responses to face-like patterns. Throughout childhood, enormous amounts of learning occur through shared attention. A child looks where another person is looking. An adult points, the child follows the gesture. Both minds become focused on the same object. This simple event is foundational. It creates what researchers call joint attention. Two individuals are not merely looking at the same thing. They understand, at some level, that they are attending to it together. From this shared focus, communication becomes far more precise. An adult can point to an animal and name it. A child can look back to confirm the reference. A person can gesture toward danger and know that another individual understands what the gesture refers to. Joint attention gives communication a shared frame, and human children become unusually skilled at it. They watch faces, follow pointing, copy actions, interpret intentions, and actively seek information from other people. This makes childhood an intense period of social learning. But copying in humans is also unusual. Children often imitate not only the goal of an action, but the exact sequence used to achieve it. Sometimes they even reproduce steps that appear unnecessary. This tendency may look inefficient, but culturally, it can be extremely useful. A learner does not always know which parts of a complicated procedure are essential. If they copy the entire process faithfully, they preserve techniques they do not yet understand. That allows traditions to survive. Imagine a tool requiring 10 steps. A child may not understand why step 6 matters. If the child copies only what seems immediately useful, the technique may eventually break down. But if the child copies the complete sequence, the method can be transmitted accurately. High-fidelity imitation, therefore, helps cumulative culture. Once a useful innovation appears, it is less likely to disappear. Another person can copy it, then modify it. Then someone else can improve it again. Over generations, technologies can become too complicated for any single person to reinvent independently. This is one of the clearest differences between ordinary tool use and cumulative technological culture. A chimpanzee may learn how to crack nuts with stones. Different chimpanzee communities can maintain different traditions. But human technologies can accumulate layers of improvement across generations until the final object contains knowledge contributed by many people. Consider something as simple as a bow. It requires knowledge of suitable wood, flexible materials, cordage, projectile design, balance, tension, manufacturing techniques, and hunting practice, no single component seems impossible, but together they form a system. More complex technologies multiply this effect: boats, clothing, traps, needles, shelters, food preservation. Each can contain accumulated information from countless previous experiments. Human culture therefore began reducing the need for every generation to rediscover solutions from the beginning. This produced a major evolutionary advantage, but cumulative culture has a requirement. Information must survive accurately enough to be useful. That means humans needed reliable learning mechanisms. Imitation, teaching, language, practice, correction, storytelling, ritual, and eventually external records. All of these help stabilize information. They prevent knowledge from disappearing when one individual dies. This also changes what intelligence means. A human does not need to understand everything personally. We can trust information produced by others. Most people do this constantly. We use tools without understanding every stage of their manufacture. We accept knowledge from teachers. We follow instructions. We rely on specialists. This creates enormous collective power, but it also creates vulnerability. If information is wrong, false beliefs can spread through the same networks that transmit useful knowledge. Humans are therefore capable of accumulating both extraordinary knowledge and extraordinary error. Culture is not automatically accurate. It is simply transmissible. Over time, societies developed methods for improving reliability: demonstration, comparison, debate, measurement, writing, mathematics, and eventually formal science. But these are recent additions to a much older system. Long before laboratories existed, humans were already learning socially, preserving traditions, and testing knowledge against experience. A hunter who consistently misread tracks would eventually fail. A plant processing technique that caused illness would be dangerous. A navigation tradition that reliably led to water could survive for generations. Culture was continuously interacting with reality. Useful knowledge could provide direct advantages. And because humans were increasingly dependent on learned information, natural selection could favor minds that were especially good at acquiring culture. This created another feedback loop. Better social learning allowed more complex culture. More complex culture increased the value of better social learning. Eventually, human survival depended so heavily on accumulated knowledge that biology alone could no longer explain our behavior. To understand a human being, you had to understand the culture around them. And this is where the gap between humans and other apes becomes especially dramatic. A human infant and a chimpanzee infant both enter the world with evolved biological capacities. But the human infant enters something else as well: a vast inherited information system, language, techniques, rules, stories, symbols, expectations, knowledge. The child grows inside a cultural environment that begins shaping the brain almost immediately, and once culture became this powerful, evolution was no longer acting only on bodies. Humans had created a new environment made largely from the behavior and knowledge of other humans. Once culture became essential to survival, humans began changing the conditions under which humans themselves evolved. This is one of the most important turning points in our story. Usually, we imagine evolution as organisms adapting to environments. A climate becomes colder, food becomes harder to find, predators change, diseases spread, and populations either adapt or disappear. But humans increasingly did something different. We began modifying the environment before it could modify us. Fire changed landscapes. Tools changed how food was processed. Shelters changed exposure to weather. Clothing changed where people could survive. Social networks changed how resources moved. And learned traditions changed behavior without requiring genetic changes. Biologists sometimes describe this process as niche construction. An organism does not simply live inside an environment. It can alter that environment and therefore change the pressures acting on future generations. Many species do this. Beavers build dams. Termites construct enormous nests. Birds create shelters. Earthworms transform soil. Humans, however, pushed environmental modification to an extraordinary scale. At first, these changes were relatively small: a hearth, a shelter, a cleared patch of vegetation, a path used repeatedly, a hunting location, a place where stone was worked. But even small changes can accumulate. A campsite used again and again becomes a familiar landscape. Knowledge attaches to places. This is where water can be found. This is where animals cross. This plant grows here during a particular season. This cave is safe. That valley is dangerous. Human environments were becoming partly ecological and partly informational. The land itself carried memory. And once people began changing landscapes intentionally, cultural behavior could influence natural selection. Consider fire. The regular use of fire provided warmth, protection, light, and new ways to process food. If cooking became important enough, bodies living inside a cooked food culture could evolve differently from bodies surviving entirely on raw food. Technology would then become part of the selective environment. Same principle applies more broadly. Humans do not adapt only to forests, grasslands, or cold climates. We also adapt to worlds created by previous humans. This interaction between biology and culture is known as gene-culture coevolution. One of the clearest later examples involves milk. Most mammals lose much of their ability to digest lactose after infancy. In several human populations with long histories of dairying, genetic variants allowing lactase production into adulthood became common. The cultural practice of using animal milk created a new nutritional opportunity. That opportunity then favored biological changes in some populations. Culture altered selection. Genes responded. This example is relatively recent, but the underlying process is much older. Once humans relied on technology, cooperation, and learned behavior, culture began creating new evolutionary pressures. The human body and the human cultural environment started evolving together. This helps explain why searching for a single moment when humans became different from other apes is so difficult. There was no one transformation. Different changes reinforced one another. Bipedalism changed how the body moved. Hands became increasingly available for manipulation. Tools expanded what those hands could do. Feet changed. Brains expanded and reorganized. Childhood became longer. Learning became more important. Cooperation became more complex. Communication became more precise. Culture accumulated, and accumulated culture changed the environment. Each development influenced the others. Human evolution therefore became a system of feedback loops, and feedback loops can accelerate change. Imagine a population in which slightly better toolmakers have a small advantage. If their techniques are copied, the advantage no longer belongs only to the original inventor. The entire group can benefit. Now imagine that better learners become more successful because tools are becoming more complicated. Natural selection can then favor improved learning abilities. Those improved learners allow even more complicated technology to spread. Technology creates stronger pressure for learning. Learning allows better technology. The cycle continues. The same process can occur with communication. More complex cooperation rewards better communication. Better communication allows more complex cooperation. Groups become capable of planning activities that would be difficult for isolated individuals. Hunting is one example. Large prey can provide enormous quantities of food, but hunting dangerous animals can require coordination. People may need to approach from different directions, drive animals toward a location break escape routes, prepare weapons, track wounded prey, and distribute the meat afterward. The exact organization of ancient hunts is often difficult to reconstruct, but archaeological sites show that later humans were capable of repeatedly exploiting large animals in organized ways. Such activities reward planning and communication, but they also reward trust. A coordinated action fails if participants abandon the plan at the wrong moment. Trust allows humans to depend on others during dangerous situations. And trust creates another interesting evolutionary problem. How do you know whom to trust? Human groups developed powerful social mechanisms for answering that question. Reputation, repeated interaction, shared identity, ritual, obligation, kinship, and visible commitment. Many human behaviors that appear symbolic may also help stabilize cooperation. A ritual performed together can demonstrate membership. A shared ornament can communicate identity. A repeated tradition can distinguish one community from another. Common stories can create shared expectations. This does not mean every ancient ornament or ritual had the same function. Archaeological interpretation must remain cautious. But symbolic behavior can clearly play important social roles in human societies. Symbols allow people to display information about relationships and identity without explaining everything verbally. A piece of jewelry may indicate group membership. BOVI decoration may communicate status. A particular style of tool may identify a tradition. Humans became surrounded by objects carrying social meaning. This is another major difference between our world and that of other apes. For a chimpanzee, an object can certainly have practical importance. A stone can crack a nut. A stick can reach termites. But humans increasingly created objects whose significance depended partly on shared interpretation. A bead is not useful in the same way as a cutting edge. Its importance may come from what other people understand when they see it. That requires a community of meaning, and communities of meaning can extend beyond immediate survival. Humans began investing time in activities that do not produce obvious calories. Decoration, music, ceremony, storytelling, burial practices, dodge-making. The existence of such behaviors suggests that human minds were increasingly occupied not only with physical environments, but social and symbolic ones. Yet we should be careful not to imagine that symbolic behavior suddenly appeared with our own species in complete form. Evidence associated with Neanderthals and other archaic humans has complicated older assumptions that symbolism belonged exclusively to Homo sapiens. Neanderthals used pigments. They produced sophisticated tools. They cared for injured individuals. There is evidence that some populations used ornaments or modified unusual objects. The extent and meaning of individual finds remain debated, but the broader picture is increasingly clear. Other human lineages were cognitively sophisticated. This is important because for much of prehistory, Homo sapiens was not the only kind of human. Our ancestors shared the world with other human populations. Neanderthals lived across much of Europe and Western Asia. Denisovans are known primarily through genetic evidence and a limited number of fossils from Asia. Other populations existed in Africa and parts of Asia. Some of these groups met, and they had children together. Genetic evidence shows that many living humans carry DNA inherited from Neanderthals. Some populations also carry substantial Denisovan ancestry. The evolutionary tree of humans was therefore not made of perfectly separate branches. It was sometimes a network. Populations divided, changed, met again, and exchanged genes. This makes the survival of Homo sapiens even more interesting. Why did our lineage eventually become the only surviving human species? For decades, explanations often focused on superiority. Perhaps Homo sapiens were smarter. Perhaps our tools were better. Perhaps language was more advanced. Perhaps we simply replaced less capable humans. Modern evidence makes the picture much more complicated. Neanderthals had large brains. They produced specialized technologies. They successfully survived difficult Ice Age environments for hundreds of thousands of years. They hunted large animals, used fire, organized living spaces, and maintained social groups capable of caring for individuals who survived serious injuries. They were not primitive failures waiting for modern humans to arrive. The disappearance of other human populations probably involved several interacting factors: climate instability, small population sizes, competition, disease, demography, interbreeding, and possibly differences in social networks or technology. In some cases, groups may not have been completely replaced. They were partly absorbed. Their descendants remain inside the genomes of people alive today. The human story is therefore not a clean victory of one species over all others. It is a story of branching populations, encounters, and mixture, and that raises a deeper question. If Neanderthals and other human groups possessed sophisticated brains, tools, and social behavior, why did Homo sapiens eventually expand across nearly every habitable environment on Earth? One possible answer lies not in the intelligence of isolated individuals, but in the size and connectivity of networks. A population with more frequent contact between groups can preserve innovations more effectively. If one community disappears, knowledge may survive elsewhere. If a useful technique appears, it can spread. If resources fail locally, distant relationships can provide alternatives. Larger social networks create redundancy, and redundancy protects culture from being lost. This idea is difficult to test directly across every ancient population, and researchers continue debating the importance of demography, ecology, and cognition, but it reveals a key principle. Human success may depend less on having extraordinary individuals than on connecting ordinary individuals extraordinarily well. The greatest human adaptation may not exist inside a single skull. It may exist between skulls in relationships, communication, teaching extant, and shared memory. By the time Homo sapiens began expanding widely beyond Africa, our species carried much more than bodies into new environments. We carried networks of knowledge, tools, fire social rules, stories, and the ability to learn rapidly from one another. That combination would allow humans to enter deserts, forests, coastlines, mountains, and eventually some of the coldest environments on Earth. But surviving in new landscapes required more than intelligence. It required flexibility. And flexibility may be the quality that ultimately made our species so difficult to stop. Human beings are not the strongest animals on Earth. We are not the fastest. We are not protected by thick fur, armored skin, or powerful jaws. Yet our species eventually occupied almost every major terrestrial environment on the planet: tropical forests, open grasslands, deserts, high mountains, cold steppe, Arctic coastlines, reem islands. That expansion was not possible because the human body evolved separately for every environment. It was possible because human behavior became extraordinarily flexible. Population entering a new landscape did not have to wait thousands of generations for biology to provide a solution. People could learn, experiment, copy successful techniques, and pass those techniques onward. This made culture a powerful form of adaptation. Consider cold environments. Humans are not naturally well equipped for severe cold. Compared with many mammals, we have relatively little body hair. Our exposed skin loses heat. Our infants are vulnerable. Without protection, extreme cold can become lethal very quickly. Yet humans eventually lived in environments where winter temperatures were far below freezing. The solution was not one biological change. It was a cultural system: fire, shelter, clothing, food storage, cooperation, knowledge of seasonal movement, and technologies for hunting animals that provided meat, fat, hides, and bone. Each component depended on learned information. A poorly constructed shelter could fail. Bad clothing could allow dangerous heat loss. Incorrect knowledge of animal migration could mean starvation. Survival, therefore, depended increasingly on receiving accurate information from others. The same principle applied in deserts. The problem was different, but the strategy was similar. People needed to know where water could be found, which plants were useful, when temperatures became dangerous, where animals moved, how seasonal rainfall changed the landscape. This knowledge could not always be discovered safely through individual trial and error. A person who experiments with the wrong plant may be poisoned. Someone who guesses incorrectly about the location of water may die before correcting the mistake. Culture allows populations to preserve solutions that were discovered by earlier generations. This creates what might be called inherited experience. You can know something without having personally discovered it, and that dramatically expands the range of environments a species can occupy. Human flexibility also came from diet. Chimpanzees are flexible feeders, but human diets eventually became far more diverse. Different populations learned to exploit marine resources, large mammals, small animals, underground plant foods, seeds, nuts, fruits, and countless other sources of energy. Tools made difficult foods accessible. Grinding could process seeds. Cutting tools opened carcasses. Fire changed the digestibility of many foods. Containers later allowed boiling, storage, and transport. Fishing technologies opened rivers, lakes, and coastlines. Human diets therefore became partly technological. We were no longer limited simply by what our teeth and digestive systems could process directly. This changed our relationship with ecosystems. A new environment did not necessarily require a new body. It required a new set of techniques, and techniques could spread. This is one reason migration became so important in human history. When groups moved, they carried cultural packages with them, knowledge of toolmaking, ways of preparing food, strategies for childcare, methods of cooperation, stories about landscapes, social rules, and language. But migration also forced those traditions to change. A technique useful in one environment may be useless in another. A hunting strategy designed for open plains may not work in dense forest. Material used for tools may disappear completely. A familiar animal may no longer exist. Human populations therefore needed both cultural stability and innovation. Too little stability and valuable knowledge disappears. Too little innovation, and people cannot respond to new conditions. The balance between the two became one of the foundations of human adaptability. This helps explain another feature of our species. Humans are unusually curious. Children explore constantly. Adults experiment. People imitate successful methods, but they also modify them. Sometimes the modification is worse. Sometimes it makes no difference, but occasionally it produces an improvement. And if social learning is strong enough, that improvement can spread. This creates cumulative innovation. A tool does not need to be reinvented from nothing. It can be inherited and then altered. Over long periods, even small improvements can produce enormous differences. A simple cutting stone can eventually become part of a complex toolkit. Wooden spears can be improved in shape and balance. Composite tools can combine multiple materials. Fibers can become cords. Cords can become nets. Needles can make fitted clothing. Watercraft can extend movement beyond coastlines. Each development creates new possibilities, and new possibilities create new environments. Humans can enter. Eventually, our species cross stretches of water that other terrestrial mammals could not cross accidentally in large numbers. Humans reached islands. Later populations moved into Sahul, the prehistoric landmass that included Australia and New Guinea, when sea levels were lower. Even during periods of low sea level, reaching Sahul required crossing significant stretches of open water. That implies some form of planned water travel. We do not know exactly what the earliest vessels looked like. Organic materials rarely survive for tens of thousands of years, but the geography makes one thing difficult to avoid. People had to cross water intentionally or at least repeatedly enough to establish populations. This represents a profound shift. Landscapes were no longer absolute boundaries. Humans could build technologies that allowed them to pass through environments their bodies were never designed to enter. Later, people reached remote islands across the Pacific using highly sophisticated seafaring traditions. Those migrations occurred much more recently, but they reveal the full potential of a much older human capacity. Knowledge can turn an obstacle into a route. The ocean is dangerous. But if people understand winds, currents, stars, boat construction, and navigation, the same ocean becomes a highway. This transformation appears repeatedly throughout human history. Cold becomes survivable with clothing and fire. Distance becomes manageable through navigation. Hard materials become useful through tools. Seasonal scarcity becomes less dangerous through storage. Predators become manageable through weapons and cooperation. The environment does not become harmless. Instead, cultural knowledge changes the relationship between danger and opportunity. But cultural adaptation has another consequence. Different populations can develop different solutions to similar problems. There is rarely only one way to survive. One group may hunt primarily with one type of weapon. Another may rely more heavily on traps. One may organize seasonal movement around particular animals. Another may depend on coastal resources. One may develop elaborate storage. Another may remain highly mobile. Human behavior, therefore, becomes incredibly diverse. Biologically, living humans belong to one species. Culturally, we have produced thousands of different ways of organizing life. This diversity can emerge very quickly. A genetic adaptation may require many generations to spread. A cultural practice can spread within a single lifetime. Sometimes an entire population can change behavior after observing a better method. This makes human societies highly responsive, but not perfectly responsive. Traditions can persist even when conditions change. Social pressure can discourage innovation. Useful knowledge can be forgotten. Groups can make catastrophic decisions. Culture increases flexibility, but it does not guarantee wisdom. Still, compared with adaptation through biology alone, cultural evolution operates at extraordinary speed, and that speed allowed Homo sapiens to survive periods of dramatic climatic instability. The Pleistocene, the geological epoch during which much of human evolution occurred, contained repeated glacial and interglacial cycles. Ice sheets expanded and contracted. Rainfall patterns shifted. Forests moved. Grasslands expanded and disappeared. Coastlines changed as sea levels rose and fell. Habitats that supported people for generations could eventually transform. Populations unable to adjust might decline or disappear. Flexible behavior became extremely valuable. A species dependent on one narrow ecological strategy would be vulnerable. Humans instead became generalists. But calling humans generalists can be misleading. An individual person does not automatically know how to survive everywhere. Someone raised in a tropical forest cannot simply walk into the Arctic and survive through biological instinct. Human flexibility exists largely at the level of culture. Different groups become highly specialized for their own environments. What makes the species flexible is our capacity to learn different specializations. The same human brain can acquire radically different bodies of knowledge depending on where it grows up. A child can learn to identify subtle tracks in dry soil, nedric sea ice, recognize edible forest plants, follow stars across an ocean, manage domesticated animals, or cultivate crops. The biological capacity is general. The cultural knowledge is specific. This combination may be one of the defining features of our species. We evolved not to know one environment perfectly at birth, but to become extremely good at learning whichever environment surrounds us. That helps explain the extraordinary plasticity of the human brain. Experience physically changes neural connections. Skills strengthen particular networks. Language shapes perception and memory. Repeated actions become automatic. The brain develops in continuous interaction with culture. In this sense, every human brain is partly constructed by other humans, parents, siblings, teachers, friends, community members, and people who lived long before the individual was born. Tools around us were invented by others. The words we use were inherited from others. The categories through which we understand the world were shaped by cultural history. Even many of our most private thoughts use a language we did not create. This makes the human mind deeply paradoxical. It belongs to one individual, but much of what exists inside it came from outside. And that may be the central reason comparing humans with other apes can be misleading if we look only at individual intelligence. Play a human and a chimpanzee in front of a simple physical problem, and the difference may sometimes appear smaller than expected. But humans rarely solve important problems alone. Behind every individual stands a cultural system containing information accumulated across generations. A person using a bow is not merely one ape holding a tool. They are using knowledge of materials, manufacturing, and technique inherited socially. A person navigating a landscape is using place names, stories, routes, and observations collected by others. Human intelligence is amplified by inheritance that exists outside DNA. By the late Pleistocene, this system had become powerful enough to carry our species across much of the planet. But humans were still living mainly as hunter-gatherers. No cities existed, no states, no writing, no industrial technology. For most of Homo sapiens history, people lived in relatively small communities and depended directly on local ecosystems. Then, only within the most recent fraction of our evolutionary history, another transformation began. Some human populations started producing food rather than relying entirely on wild resources. Plants were cultivated, animals were domesticated, settlements grew, populations increased, and eventually, cultural evolution began changing the planet on a scale no ape had ever approached. The biological differences separating humans from other apes had accumulated over millions of years. But the world we recognize as civilization would emerge with astonishing speed. And that sudden acceleration reveals perhaps the most important fact of all. Human evolution did not end when modern humans appeared. The process simply changed its most powerful engine. The distance between humans and other apes was created over millions of years, but the world separating us today was created mostly by culture. For the overwhelming majority of human existence, Homo sapiens lived without cities, writing, states, machines, or agriculture. People hunted, gathered, moved through landscapes, raised children, built shelters, made tools, sheared food, told stories, and learned from one another. Biologically, those people were already human. Their brains were not waiting for civilization to make them complete. The great transformation came from what those brains were able to accumulate together. Around the end of the last ice age, some human populations began changing their relationship with food. Instead of relying entirely on wild plants and animals, people in several regions gradually began cultivating certain plants and managing certain animal populations. This did not happen once. Agriculture emerged independently in different parts of the world, involving different species and different local histories. The process was slow. There was no single day when hunter-gatherers suddenly became farmers. People experimented, returned to useful plants, protected favored species, changed landscapes, stored food, moved less frequently. And over generations, some plants and animals changed genetically as a result of human selection. Domestication was another example of gene-culture interaction, but now operating across multiple species. Humans changed wheat, rice maize, cattle, sheep, dogs, and many other organisms. Those organisms in turn changed human societies. Food production could support larger populations in some environments. Settlements became more permanent. Stortron became increasingly important. Property relationships changed. Labor could become more specialized, and population density increased. But agriculture was not a simple improvement in every respect. Early farming populations often experienced new problems. More repetitive diets, greater exposure to infectious disease, hard physical labor, social inequality in some societies, dependence on a smaller number of food sources. The transition was therefore not a straightforward march toward a better life. It was another complex transformation with both advantages and costs. Yet once large settled populations existed, cultural evolution accelerated, specialization could expand. Not everyone needed to spend the same amount of time obtaining food. Some people could concentrate on particular crafts, construction, metalworking, trade, administration, religious roles, warfare, medicine. And eventually writing. Writing was one of the most important extensions of human memory. For hundreds of thousands of years, knowledge had depended primarily on living minds. Language allowed information to survive through storytelling, but memory remained vulnerable. People forgot. Stories changed. Experts died. Writing altered that limitation. Information could now survive outside the brain with far greater precision. A record could remain after the writer died. Instructions could travel without the person who created them. Accounts could be compared. Laws could be preserved. Mavigments could be recorded. Knowledge could accumulate across generations without depending entirely on oral transmission. This did not instantly create science or modern civilization. Early writing systems often served administration, accounting, ritual, and political purposes, but the deeper transformation was enormous. Human memory had become external, and once information could be stored outside the brain, the amount of knowledge a society could preserve expanded dramatically. Libraries later multiplied that effect, then printing accelerated copying. Scientific institutions created systems for testing, criticizing, and preserving ideas. Modern communication technologies eventually connected billions of people. At every stage, the principle remained similar. Human intelligence became more powerful when information could move between individuals and survive across time. This is why comparing the brain of a modern human with the brain of another ape tells only part of the story. A modern person does not face the world with one brain alone. Behind that person stands an enormous cultural archive, language created by previous generations, mathematics developed across centuries, tools refined through countless experiments, medical knowledge accumulated from millions of observations, maps produced by people who explored places we have never seen, scientific ideas tested by researchers we will never meet. Our individual intelligence is amplified by collective memory. This is why a person today can perform tasks impossible for even the most brilliant human thousands of years ago. The biological brain has not been redesigned from scratch. The cultural environment has changed. A child born today can learn to operate technologies that would be incomprehensible in prehistoric life, not because the child belongs to a new species, but because the child grows inside a radically different information system. This gives human culture a strange form of power. It can outrun biology. Genetic evolution continues. Human populations still change genetically. Natural selection has not stopped. But cultural change can happen so quickly that environments may transform several times within a single lifetime. For most species, such rapid environmental change can be disastrous. Humans often respond by changing behavior instead of waiting for genetic adaptation. New tools, new clothing, new buildings, new medicines, new rules, new sources of food, new systems of communication. This flexibility is one of our greatest strengths. It is also one of our greatest dangers. The same cultural system that allows humans to solve problems allows us to create problems on unprecedented scales. Technology can increase food production. It can also destroy habitats. Cooperation can build cities. It can also organize warfare. Shared beliefs can create trust between strangers. They can also divide populations. Knowledge can cure disease. It can also create weapons. Human culture does not automatically move toward wisdom. It increases capability. What humans do with that capability depends on social systems, incentives, knowledge, and choices. This is important when asking why humans became so different from other apes. The answer is not simply that we became more intelligent. Intelligence alone is too vague. Chimpanzees are intelligent. Bonobos are intelligent. Orangutans solve complex problems. Gorillas learn. Many animals remember, communicate, cooperate, and use tools. What changed in humans was the interaction between multiple abilities. We became highly dependent on social learning. We developed unusually powerful communication. We extended childhood. We increased cooperation. We became skilled at shared attention and teaching. We preserved innovations. We connected groups. And we accumulated culture. Each generation inherited not only genes, but a growing library of behavior. That library became a new kind of evolutionary inheritance. This helps explain one of the strangest facts about our species. A human raised without access to human culture would not spontaneously invent the modern human world. No individual could. No person independently discovers language, agriculture, metallurgy, writing, mathematics, electricity, and medicine from the beginning. Civilization is collective. It is built from layers of knowledge created by countless minds. The difference between humans and other apes therefore cannot be found entirely inside the individual. It exists partly in the network connecting individuals across time. A chimpanzee may learn from its mother. A human child can learn from a teacher who learned from a book written by someone who studied discoveries made by people who died centuries earlier. Information travels through chains of minds. That is extraordinary. It means the dead continue teaching the living, and the living can leave information for people who do not yet exist. Culture allows minds to communicate across generations. Writing made that ability more precise. Modern technology has made it almost instantaneous. Today, a discovery made on one side of the planet can reach millions of people within hours. Humans have created a global information network far beyond anything evolution produced biologically. And yet beneath all of it, the ancient ape remains. Our bodies still carry primate anatomy. Our emotions still reflect social pressures shaped in small groups. We care deeply about status, belonging, trust, fairness, family, reputation. We form alliances. We fear exclusion. We imitate others. We seek approval. We become curious when others possess information we do not have. Modern civilization is built by minds shaped in a much older world. This mismatch explains many features of human behavior. A brain evolved to track reputation inside a small community now reacts to the opinions of thousands of strangers online. A desire for calorie-rich food that was useful in uncertain environments now exists inside societies where such food can be constantly available. A tendency to divide people into social groups can operate inside nations containing millions. Ancient psychological systems continue functioning inside environments they never evolved to encounter. So why are humans so different from other apes? Not because evolution suddenly produced a completely new kind of creature. The differences were assembled gradually. An upright ape with increasingly skillful hands, a growing and reorganizing brain, a long childhood deep dependence on others, powerful communication, intense social learning, and an extraordinary ability to preserve what previous generations discovered. None of these traits alone explains humanity. Together, they created something new, a species whose primary adaptation is not a claw, a tooth, a wing, or a shell. It is the ability to accumulate information collectively. And once that process began accelerating, the gap between humans and every other living ape widened far faster culturally than it ever could biologically. The chimpanzee looking back at us is not a primitive version of a human. It is the product of its own evolutionary history. Just as we are, our lineages separated millions of years ago, and both continued evolving. The remarkable thing is not that one became higher and the other remained behind. Evolution has no ladder and no predetermined destination. The remarkable thing is that one branch developed a way for knowledge to accumulate so powerfully that it began reshaping the entire planet, cities, books, music, mathematics, spacecraft, medicine, computers. All of them ultimately depend on a chain of humans learning from other humans. That chain stretches backward far beyond civilization, beyond agriculture, beyond writing, beyond our species itself, back to ancient primates, watching one another, learning from one another, and surviving together. The difference between humans and other apes did not appear in a single moment. It was built slowly. Then culture made it accelerate. And today, when we ask what makes us human, perhaps the most accurate answer is not simply the brain. It is what our brains can build together.